坐在当时，树在触到这个，好了，那你主角啊？
still got presentation. Come on.
This assignment.
Only this assignment the last one.
Yes.
So you got plenty of time.
Huh? So we need to prepare exam, man.
Yeah, you're going to prepare this, you also prepare for the exam.
After next week start already.
Yeah.
I got 2 paper.
Are you finished by today? Okay, chapter 10 and 11, we'll go on our way. 10 is about graph. But it does not talk about, it talks about graph. Actually, it has part of the algorithm subject. But there's nothing about parallelism. It's about graph. No, it's more of an algorithm. I think it should be in the algorithm subject. Yeah, tree graph. And then you got the algorithm search.
That is data structure algorithm.
Yeah, data structure algorithm. So you study there, alright. This one should be excluded because there's no. I don't see any anything included inside there. Okay. Now the last one is about QRAM, about memory that is used in GPU. I will not cover that as well. Okay. So this is the last slide.
怕时间已结束了。
This chapter 9.
By the way, question is, this kind of the error is not depend on.
No, that's not that long. That is the computer crash. Your operating system crash.
It is threats starting divided by
That means your thread actually has bug inside it. The device driver that you install has bug inside and then crash the operating system. Because operating system provide device driver some privilege. And that privilege somehow is being misused in a certain way, and therefore your operating system crash. If your program crash, because your program is running in lowest privilege, so even though it crashed, the operating system is not harmed. But device driver, when you get harmed, the operating system will crash as well. Yeah, actually, it does not have the highest privilege. Highest privilege is privilege 0. That's operating system. Only device driver is privilege 1 or 2. But somehow it's able to crash the operating system. It's kind of weird also. But it has the privilege to destroy the system. This is the last part right here. I think I covered the important part of it, which is how you share your workload among the power computing so that you have the widest distribution. Okay, and also the shortest path length. The shortest path length means you want it to be short as much as possible, but as wide as possible. If it is wide, that means you can run more parallel. That means you can parallelize the computation. The height actually determines how fast it can accomplish the job. Okay? So the shorter it is, the better. The wider it is, the more parallelism, the better. Okay? Actually, this one should come much earlier, but unfortunately the stuff will not appear here. This one you have been doing in your practical, and of course also in your assignment, you are actually doing this as well. Okay? So most of our framework that we use is single program, multiple data. That means you got one program running the same code, but the data are different. Okay? And in this kind of model, you have one master normally, and the rest are workers. As you can see from OMP, the master thread is running. When you enter into the OMP parallel partner, you have workers that is actually working together with the master to accomplish the job. Okay, and then what we can improve is actually the parallelism that you can improve the performance is actually lies in the loop. So that's why you look into the loop whenever you want to improve your performance gain. Okay, see just now when we did some of you did the presentation. I'm not sure whether you noticed or not. Some loop is within the parallel computing, but some loop is outside. When I see that for loop is outside, I already know that something is not right. Okay? Because that is a place where you achieve parallelism gain. Right? And once you finish performing the job, you join. But basically here, they're not sure, I think down below it shows that you have to distribute the work first to the worker in order to allow it to work on the job. Okay? And then here is where all the worker works in parallel. And before you join, actually you have to gather together the data first before you join. Okay? So that is the programming models, the program side model. On the data side, either you share the data, especially OMP, you share the data in the memory. If it is MPI, then you have to send over the network through message passing. Okay? Another kind of model, which I believe some of you are doing, using shared queue, especially those do compression, data compression, encryption. Okay? You put it into the queue from one end to the other end. That means you've got workers that is working just like in the factory. Okay, in the factory you see one worker, let's say a car factory, right? Okay, maybe this worker is assembling the tires. This one is the body of the car. Okay, this one is the windshield, for example. Okay, and then this one maybe is the, I'm not sure, maybe the engine and so on and so forth. And eventually, this is the car. Okay, the final result. Alright? So when you come in time, maybe there's only skeleton here. This is the frame of the car. Okay, and then it gets into here where the thread or the worker is actually installing the tires only. So the worker here actually has a specific job to do. Okay, they only assemble the tire, doesn't do anything else. Okay, but when you complete the time, the car is still not a car, it's just a skeletal frame with a tire on it, right? But eventually when you get through this line, when you come up here, it's actually a complete car. Okay, so you see each worker actually focus on one thing and they are good in doing that only. Okay, they don't worry about anything else. So shared queue here basically means this. I have this this car, and this car gets passed to this guy. Okay, and the car that the skeleton frame with the tire just now that this worker is doing is passed to this other thread to put in the body, right? So that this skeleton, the new skeleton frame of the car can come in so that I can install the tires, right? So basically this is the key, the shared queue that we are talking about. So how many shared queue you have? 1, 2, 3, 4, and so forth. Okay? So this queue, this shared data is normally shared among all the workers. If you have n workers, mostly is shared by n workers as well. But shared queue is different. Shared queue normally is very limited. For example, here is a 1-to-1. But it can be something like this. You got your team, maybe a team of 5. That means you got 5 lanes here. First lane, second lane, third lane, fourth lane. So not only you are doing the tires, your partner, your friend or your colleague is also doing the tires. So these are different lanes, right? Okay. But what you can do perhaps is this, because some of you might work slower than the rest. You might not have the individual queue, but one queue. Okay, one queue that is shared among your colleague. So whoever that is finished will go into the same queue, and whoever that finish his job assembling the tire will get from the queue. Okay, if you are faster, then you get more. Okay, it means depends on who is fast. Okay, so you got only one queue, but you got multiple receiver, multiple sender. But it can be one sender, one receiver as well. Okay, so shared queue normally is 1-to-1, but in this case here you can have multiple sender, multiple receiver. Okay, so you can be n as well, n number of workers, but normally it is much lesser than the shared data. Okay. Now distributed array is kind of chaotic one. This one is organized because you have the input and you know who is the output. Okay. Distributed array is just the array like that, and then whoever finishes just put into the empty slot. Okay. Then on the other side, it sees any non-empty slot, you just get it. Okay, so this is kind of random way to share the data. Okay, you put data into the slots that is available. On the other side, you just grab from whatever slot that is not empty and process the data. Okay, so there are many kind of models. This is not just the only model that we have, but these are the most common models that we use, especially the first one. Okay, this one also very popular, and in fact, this can be seen by some of the example, the assignment example. Okay, the programming models, the single program, multiple data, all the processing element or the processing engine execute the same output, what I mentioned to you, but it doesn't share the data. The data can be different. Okay, so each processing element or processing engine has its own unique ID, so that you can recognize or you can tell this unique ID what to do. Okay? It can access a portion of data. It doesn't access most of all the data. For example, in this case here, it's only accessing the tires, right? It does not access many other data, but it can do the job. Okay, different PE can follow different path through the same code, because you can have if-else statement, right? For example, if this ID does not match, don't do this. You do the other part, right? So these are what you can do, even though it is single program, multiple data, but some PE can run certain part of the code, but not some other part of the code. Okay, this is essentially the CUDA model, and in fact, not just CUDA. NPI is using that. NP also uses it. One thing we did not discuss is OpenCL. Okay? OpenCL is another framework that we can use to do cloud computing, but it's not covered in our subject. Okay, so SDMD is the most common one, but of course, other model is also common. For example, single instruction, multiple data. This is actually used in the past before GPU took over. In fact, all our computer has this single instruction multiple data. Okay, so your register is going to be very big. You got 412 bytes of register. The size is 512 bytes. Okay, and of course it can be split into multiple sections, and you use one single instruction, and then you have multiple data that is processed at the same time. So that instruction execute in one clock cycle. Okay, so this is the equivalent in processor level to our SDMD, which is at the programming level. Okay, so the name looks different, but actually they're the same. This is at the processor level. This is at the programming level. Okay, So this single instruction of data and single program of data is kind of equivalent. Alright, and then your master and slave, or master or worker. So the master will set up a pool of threads. You can set it up in OMP or API, how many threads to run. Okay? In OMP, you set it in your program. In API is the program that you start to execute, is the one that you put in how many workers to run. Okay? Okay, so in most of our case, the master and worker, they run the same code. Only the master is the one that actually coordinate, okay? Coordinate the execution overall. Okay, and then loop parallelism is, as I've said many times before, since we got multiple workers, we can assign to a single instruction set that does not loop, but that will not give us any performance gain. If you want performance gain, look at the loop. Because if you spend your time doing parallelism in loop, you can actually get performance gain. But of course, you have to look at the loop, whether you can actually do parallelism. Like what we have seen before, some you cannot, some you can. The one that you cannot, you have to look closely, whether it is a false, true, or false. Remember? If it is false, that means you can improve. If it is true, that means you can't improve anymore. Okay, so you have to look into your code and see if you can make any adjustment so that you can do loop parallelism. But most of the time you can do. Okay? And finally, once you are done with that, we gather the data and also join together. Join here means everybody come to a point where they wait for one another before they end or terminate the program. Okay, SPMD is the most dominant coding style for parallel computing. There are many others, but then these are the most common ones. Okay, we use this model to solve quite a number of our problems. Okay, and especially when we use CUDA, it's already using this SPMD. So if you want to use any other techniques, you might not be able to take advantage of the CUDA. Okay, so if let's say a problem is not this kind of format, then you have to adjust it. Okay? Adjust it so that it becomes SPMD. Okay, the main advantage is because you have, especially the availability of GPU, you can get it off the shelf and you can buy it at the moment. It's kind of cheap also, although the price is increasing. But you can buy off the shelf this hardware in order to perform the task or gain the performance gain from them. Okay? And one of the other advantage is that the source code is only one piece. Okay? There's only one source code that you have to worry. Make sure that it works. Okay? In other kind of model, we have multiple program, multiple data that is quite chaotic because you need to worry about different parts of the code and making sure that they are able to function together. But if it is a single code, normally it's much easier to ensure that the code are correct. Okay, because we only focus on one code. Okay, these are the typical phase that SPMD program has to do. As you all have seen before in your assignment, first you have to initialize. Must make sure that either the framework is initialized, and also your data structure that you use to process the data must be initialized as well. Second thing is, because you are working using SPMD, every thread is actually running the same code. So you need to have unique ID for each one of the thread or core that is processing the data. Okay, you need to identify which core it is. Okay, so that we can use that in order to identify which thread is supposed to do which part of the code. Okay, let's say thread 0 should do data 0, thread 1 should do data 1, right? So you need to have a unique identifier in order to distribute this data for SPMD. Okay? And then you need a way to distribute data, decompose the data, okay, and send to the threads to do. And there are multiple ways. OMP is one way. OMP is using the shared memory to decompose, so it's very efficient. MPI is not so efficient, but it can be used for multiple or across a number of PCs, okay, because it is using message passing rather than shared memory. Okay, you cannot have shared memory sharing of data with your multiple PCs. Okay, only MPI can do that. Unfortunately, I think we don't have time to actually show or experience the MPI which is using multiple computers rather than a single computer like what we have done in practical. Okay, after you have distributed the data, or you decompose the data, and you replicate whatever that is necessary, then you start the computation. That is very obvious. This computation is done in parallel, of course. If you don't do it in parallel, you cannot get the performance gain there. Okay? And before you finalize, actually there's a missing part there. You not only finalize, you have to collect the data first. Collect the data here. Because you distribute, you do the work, you have to collect the data. So that's missing there. Okay? And finally, once you've done the job, then you finalize it. Okay? So the important part is actually, apart from initialize and finalize, is in between, which is first, identify who you are. Okay, this identification will tell you which part of data that you need to do, and then you do your computation, and then you gather the data. Okay, finalize your platform. Okay, the track ID is used to identify who the core is, like what I mentioned just now, and to be able to know which part of data that you should use in order to process. It's not very mentioned just now, so I'm not going to repeat it. And of course, what we have done with our studies is actually to get our improve our processing time. As I can see, some of you have achieved quite a great performance gain, right? We had a group just now, I saw how many times your performance gain?
How many?
100 times faster GPU compared to a single thread?
I think even more than that.
More than that, close to 1,000, or less than 1,000.
If compared to OpenMP,
No, compared to the single core,
compared to the single core,
close to 1,000. Okay, so you can see yours about close to 1,000, and the first group on Monday also quite good result. They showed me, the group showed me 200 times better. Okay? Maybe his one is a bit tougher. There is some kind of data dependency. His work has data dependency. But then even though with the data dependency is able to improve the speed to 200 times. Right? But of course, you can still improve that. You will check certain part that you can improve. Okay, that will not be computation or something that is repeating. Okay, you can actually substitute it and you can get much more performance gain. Okay, even though you got performance gain, okay, it doesn't mean that you increase the number of processor or the cores, you will not get a linear always increasing performance gain. Okay, so if you look at the graph, of course you will expect like this. This is the n cores. Right? As you increase the number of cores, this is a performance gain. Right? We would expect it to be linear like this, right? But we don't get this. Okay? It seems like if we go to infinity, this performance gain also will go to infinity. Actually, it's no. You see something like perhaps like this, okay, which is more. The rarity that you get is more of this kind of shape. Okay? So what we expect is like this, straight line, but actually we don't. We get something like S shape like this. Okay, so here it shows to you that you already saturate. When you increase the N, the number of processors that is increased, but performance doesn't increase much. Either it stays stagnant or it doesn't change, it will increase slightly. That's all. Okay? That means you go to infinity, it does not gain much. So your actual performance gain, the best money, bang for what we call it, is right up to here only. It means you spend this much money to get this performance difference. But after that, you spend more money, you don't get any much gain there. Okay? This is an unfortunate case, and this actually been summarized by a guy called Amdahl. This is the formula that we talk about here. Okay, Amdahl is a computer scientist. Sorry, I think he's a mathematician, a physicist. He described this Amdahl's law. I mean, he described this phenomenon, and then we call it Amdahl's law in honor of his discovery about this. So if you say this is not true, okay, what you get is what happens is like this, and this formula actually describes this curve. Okay? Right. Before I go into that, let's study a little about this. Okay, you see this part here, even though you are using multiple processors, right? You can see that actually when it starts, the time is kind of slow, but it's exponential. But after some time, it actually doesn't improve much. Okay? So what is happening here? We expect it to be linear, right? But it is actually lower than the expected result. The reason is because at this lower end here, right? If we share the data to a small number of core, you don't get any much performance gain because of the overhead. So here you actually spend time doing the overhead stuff, so you don't improve much. But then as you increase the number of threads, the overhead is less dominant. Okay? The number of cores actually overcome. So that's why you get this much of performance gain. Right? But after a certain time, we find after a certain number of cores, you don't see any performance gain anymore. Okay, this one is easily described. It's just like you have this amount of data to do, right? And you can split very nicely to, let's say, 10 people. 10 people to do. Okay, for that amount of data. Okay, you split to 10. You can perform very fast. But then, if you increase more to 20, you find out that you cannot split some of it. So the other guy is actually not doing anything much. That's why you don't see any performance gain. Okay? Because your data can be only processed by that number of people, right? So if you increase, let's say cleaning the toilet, for example, maybe if you put 2 people there, you increase, 3 people increase. But then after a while, you find out that there's no improvement, right? Because so many people are inside the toilet, basically they are hindering one another from doing the job. So the performance actually does not increase, but stays stagnant. Okay? So that is what this Amdahl law is talking about. Okay? As you increase, you don't get any performance gain there. Okay, so let's look at the terminology there. Now this terminology is described very, the term or the notation is described here, but I will not go into this because it will talk about the term that we use, and we can actually, if we arrange that in a certain way, it has certain meaning. Okay, but I will not go into this. I will just go to the most important part only, okay, which is this equation. But before I get into that, let's look at what is the meaning of this one. Okay, S, P, and N. So I'm going to talk about this first. So S, what is S? S is the serial part of your computation. That means it cannot be used, you cannot use our computing to run that code. Okay? So it's a sequential fraction or the serial fraction, part of a task that you do that you cannot parallelize. It can only be run in serial. Right? There's a certain part that you can run in serial. For example, let's say you're reading from a file. Right? You're reading from a file. You don't want too many people to read from a file. You want one person to read from a file. And then that master thread is going to distribute the rest of the worker to do the job, right? So that might not be able to be parallelized. You have to use one master worker to actually do it, right? So that is the part which is the sequential fraction. That means that part of the task cannot be run in parallel. You have to run in serial. Okay? Now, how about the parallel fraction? The parallel fraction is the fraction of code that can be parallelized. Right? So, if let's say you take 100%, okay, let's write it down. If your code is 100%, of course, your code, full code is 100%, right? Now, a portion of it, let's say 20%, cannot be parallelized, so you have to run in serial. That means one thread when you run this. You cannot run in parallel. Okay? That means the rest, 80% can be parallelized, right? You can run in parallel. And when you add this to, it's 100%. Understand? Okay? So whatever that is given here is in fraction. Okay, it's in percentage, this one is fraction. So in fraction, this one means 0.2. This one means 0.8. So when you add up these two, is 1, isn't it? 1.0. Is it correct? Is it correct? Whatever that is not serial, it must be parallel. Whatever that is not parallel, must be run in serial. Is that correct? So it's 100%, isn't it? Okay, in fraction, if this is 0.2, this must be 0.8. So all must be 1. Okay? So if I specify my serial fraction is this much, then my parallel must equals to 1 minus s. No, 1 minus 0.2 is 0.8. Is it correct? So that is what this is trying to say. Okay? Now the rest I'm not going into it because our formula later will not have that. But I'm going to talk about this m here. This m is the speed up that you think is you're going to achieve. Okay? For example, this line here, this blue line here, is the one that you can achieve, right? If you increase twice the n, you will see performance gain also twice as much. Okay? So that is the n. Okay? So it's equivalent to, actually it's kind of equivalent to the number of processors that you have there. But it does not really translate to this kind of time at the end, because as I said before, even though you can increase the number of processors, you might not get the performance gain to increase linearly. Okay, it will stay stagnant like this, right? So the n that I was talking about just now is the n that we think that is going to increase our performance, our speed up performance, or we call it fraction of improvement. Okay, fraction of improvement. But this is the overall improvement that is achieved. Okay? Okay, so let's see this curve here. So how do we define this curve? Okay, this curve is if you run it in serial. Okay? If you run in serial. Right? And then if you run it with serial plus parallel, isn't that this speed up? Performance gain? Oh, okay, it's called speed up. I always call it performance gain. Isn't that speed up? It is, right? This one run in serial, completely in serial. The bottom one is, of course, if you want this to be parallel, but not all can be parallelized. Remember I mentioned to you, not all can be parallel, right? So you got some serial, then you have to run in serial. The rest will be run in parallel, right? So it is serial or parallel. Isn't that the speed up? The one that you compute. I always tell you that compute is parallel, the performance gain. Actually, you are computing this. Isn't it? Okay? So let's see what is this serial. Remember I mentioned to you that the fraction of code that is run by serial code, isn't that S? It's S, right? Now how about the P? Is the fraction that is you can run in parallel. Is that true? So you distinguish these two. The one that you cannot run in parallel, you have to run in serial. This one you can run in parallel. But even though you can run in parallel, you also can run by a single thread also, right? Isn't it? Right? So that serial here is going to be run by a single thread. This one can be run by parallel, but you run with a single thread. That means you get this, right? Understand? Okay. How about the bottom one? So this one is S plus P. The bottom one is S, the serial, plus P, but then you distribute among the processor. This one is the one that you run in parallel. This one, actually what you do is you run is parallel, but you run only one thread. So P divided by 1. Okay? So eventually your speed up is equivalent to S plus P divided S plus P divided by N. That is the speed up. Do you agree? Your code can be split into two parts. The one that can only be run by serial. The other part you can run in parallel. Okay? So if you use single thread, the serial, of course, you have to run in one thread only, right? The parallel, because it's serial, you run in one thread. This is what you do, alright? I always tell you compare with the serial, one thread. So basically you're computing this. S P divided by 1 is equal to S plus P. Now the one that you run in parallel, but not all can be run in parallel, so this S is there. But this one, you can run in parallel, and you have multiple cores. Let's say you got N cores, then you divide by N. And eventually this will be greater than 1, right? Or equals to 1. That is performance gain, isn't it? So do you understand this formula? Okay? So you don't have to memorize this formula. You just remember what I said. Okay? If you remember what I said, it's much easier than looking at all those terminology out there, because it's going to be very messy and make you hard to understand and remember. And this is how I remember it. Okay? Now, the rest of the formula, it might be useful because later on you'll see that the question that will come out will not be so easy like this. It will give you in different kind of term, and you need to know their different identity. Okay? You see, they're all the same. Just that the identity is different. Okay, it's kind of simple. Remember I mentioned to you, the serial plus the parallel is a whole code 100%, right? But this one is in fraction. Okay, for example, this one is 0.2, this is 0.8, overall is 1. If you take the serial plus the parallel, it's always 1, isn't it? It's always 1. S plus P is always 1. Is that true? The serial part and the parallel part, when you combine, is the whole code, isn't it? It's 1, 100%. So it's always 1 here. S plus P is always 1. Okay? And then S plus Pn. So this formula is the second formula that you see here. Clear? It's a different identity, but it's describing the same thing. Okay, why I show you this? Because some of the question does not appear like this, appear like this. So by remembering this, then you know how to substitute it and get the answer. Okay, I'll show you some example now. Okay, thanks. If you multiply the top with n, you multiply the bottom with n. Okay, what I mean is you do this. n by n, isn't that they are the same? Because n divided by n is 1. Anything you multiply with 1 is the same identity, isn't it? So you get n as n plus p. So this is the third equation that you see here. Is that clear? So it's nothing special, it's just playing with it. And why I showed you this identity, as I said before, the question normally don't come out exactly like this. Sometimes in a different form. But then if you remember this tree identity, it's easy for you to actually plug in and answer the question. Okay? Okay, now I'm going to here what this equation is telling you is it means that if you increase the processor, it doesn't mean that the performance will increase. No. Sometimes we increase up to a certain point, it does not increase anymore. Okay, it becomes less efficient. Up here, it will become less efficient. Okay, now, of course here it is very efficient because you got performance gain there. But as it increases more, it does not increase anymore. Okay, the question here is this: since Amdahl's law says this, that means why do GPU keep on increasing the number of cores? You increase the cost, you pay a lot of money, but you don't get anything out of it.
So ask NVIDIA why they make great.
So you have to ask NVIDIA why they increase the cost. One thing is market. Of course, you have to show the truth as well, right? So can we combat this? Can we overcome this problem? Luckily, yes. There's another law down below. It's called Christophor's law. He actually noticed something. He said, hey, actually not really true. Yes, this is true. If your problem size is fixed, yes, you're going to get this. But if you increase your problem size, this one will scale as well, will go bigger as well. As the number of the core increase, you will get the performance gain. So Amdahl's law is only looking at this. We described it. Say, if I increase the number of processors, but I fix my problem size, up to a certain point, it will saturate and it will not increase further. It will keep on increasing. Christophor's law says this. He said, in order to combat this, of course, we want to combat this, right? Because in the future, we want to have more and more GPUs, cores in our processor, right? If we are stuck here, there's no point to increase the GPU. The number of cores. But Christophor's law says this. No, actually, no, not true. Here, if you fix your problem size, you get this problem. But if you scale your problem size, then this will increase. Which is quite true. So remember the toilet I was talking about? If you cram 100 workers, toilet cleaner in the same toilet, will it increase the efficiency? No. But if you have more toilets and then you distribute this worker, you'll be more efficient, isn't it?
More dirty.
Right, yeah, more dirty is true, but then you have more toilets and we can assign this more n to solve the problem. Okay, so it means that here this Amdahl's law only focus on fixed problem size. Okay, that's why nowadays you see that people talk about big data. Why do they talk about big data? Big data is because by scaling the size of data, then you have n core, the performance keep on increasing. As you have more cores, it doesn't mean that you want to stagnate. No, it's going to increase this problem. Okay? As you have more data, you have more performance. That's why I always tell you, don't look at small size, look at big size. Because if you look at big size, then actually you will not get trapped in this kind of problem. Okay? You will not get trapped in this problem. Because if you, let's say for example, you've got 1,000 cores. If your problem size is too small, you'll get trapped there. Okay? So you want to scale to 1,000, you have to increase your size. Okay, so that's the reason why I mentioned to you to use big data so that you can show your performance. Because sometimes when you see, oh, performance not good, and then you get demotivated. Right? Okay, you you want to see performance gain, right? So use big data in order to get the performance gain. Okay, so let's look at an example. A question that can come out. What kind of question? Okay, the speed up here is the performance gain that I was talking about. Here is called speed up, right? So execution time before the improvement, meaning that you run everything in serial, including the parallel code that possibly can be parallelized, but you run using a single thread, right? So that is before you apply parallelism, okay? And then you divide by the execution time after you have time improvement. That means you apply this parallelism, okay? Okay, there are three types of problems to be solved in the following columns. Amdahl's law equation. Okay, this equation is the same equation that you see here. The first one is the one that I derived to this point here. From our understanding, we get this. We can understand this, right? Now, the most common equation that we use is actually this here. So, but here is showing to you this, the second one. Okay? So, one is this one here. Okay, and this 1 minus fraction is fraction enhanced is this S here. Okay, why is it different? Okay, let's have a look. Remember I mentioned to you your zero part fraction of your code plus the current part of the code is 100%. Is it correct? That means your S is equal to 1 over minus P. Is it correct? So that means I can replace this with this. I can replace this S with this. 1 minus P. Is that right? Is it right? So this 1 minus P is this one. 1 minus the fraction enhanced. So this fraction is the one that you can enhance, which is the one that you can run in parallel. So, fraction enhanced is this P. Understand? Just that it does not show in this form, but show in this form. Show in this form. Okay, plus the fraction enhanced is the fraction enhanced is the one. Actually, these two are the same. Fraction enhanced. Right? Divided by the factor of improvement. Remember, I draw this diagram here, the N, and I show you this. This is the factor of improvement. The one that you think is you're going to achieve, but actually you won't achieve that. What you're going to achieve is this actual. This is the one that you think is going to achieve. This is the actual that you actually achieve. Understand? Okay? So, and that is the N. Okay? The N that I was talking about. Okay? Why did I say that is the one that you think? Because you remember, P divided by N. As I increase this whole number will decrease linearly over time. It seems that I go infinity, this performance will go very, very good. You go to zero. When you go to zero, it means that I have a lot of performance gain there. Because I solved the problem in 0 time. But that is not achievable, right? Okay, that's why I say this N here is the one that you think is you're going to achieve. This speed up is the one that you get in reality. Okay? You can think of that. Okay, so the question can be of these 3 forms. Determine S given FE. FE is this one, fraction enhanced. Fi is this one, factor of improvement. Okay? So that Fi is our N. Okay? And P is our fraction enhanced. Okay? So determine the S. The S is actually this speed up. Okay? That means determine the speed up given the P and the N. Right? So if I give you these two, you should be able to determine this S. Okay? The other 2 questions that most probably we want to ask is, we want to find out what is the factor of improvement given the speed up that we get actually that we get. And the code, the fraction that we can parallelize. Okay, given these two information, we want to find out what is the factor of improvement. This n. Okay. The third one is we want to find out the factor of enhance, which is called p, which is our p, given the speed up and also given the factor of improvement, okay, which is n. Okay, so let's look at the three examples. This one actually came out in last year exact. If I'm not mistaken, I did not set the questions on the last because I did not teach last year. Okay, so we want to find S. We know Fe, which is fraction of fraction enhance, and fraction of improvement. We want to find S. Okay, let's look at the example. Let the program have 40% of this code enhanced. That is, we know that Fe must be 0.4. Okay, and normally it will not tell you this. We just tell you this only. So you need to know that Fe is 0.4. Okay? And it runs 2.3 times faster. This one is kind of confusing. This is the one that we think that it can increase in performance. It can run this fast. Although it looks like speed up, right? Actually, it's not the actual speed up that we get. This is the one that we think it will give us the speed up, which is our n. Okay? 2.3 times, which is our factor of improvement. So what is the overall speed up? This is the one that actually we will get. Okay? So we apply the formula, it's quite straightforward. So 1 minus Fe, we saw that in order, it was 1 minus Fe plus Fe divided by Fi. Okay? Whenever you get that, you put the value inside, you solve it, and you get it. Okay? So speed up is, actual speed up is 1.292. And this value is always smaller than this. Okay? It's always smaller than this. Remember I mentioned to you that this is the one that we think is we're able to get. But no, you don't get that, you get this. Okay? So it's easy to check whether your answer is correct or not. Always look at this. If it is bigger than that, you know that your answer is wrong. It must be smaller than this. Okay? So that will be the answer. So it's quite easy, right? Okay, one thing, formula is not going to be given, you have to remember. And how do you remember? Remember like what I explained to you just now. Okay? And the rest is just logical understanding of what each one means, and then you just substitute it and get the rest. Okay? Okay, so this underscore actually, the question that comes from here actually is very simple. But this, it can be complicated if you try to analyze the whole thing. Because all those actually is important, but you can actually derive from the understanding. But the core is this one. Okay? Okay, the second question is to predict the speed up of fraction enhance. That means given these two, the fraction enhance, and we know the speed up, we want to find out the fraction of improvement. Okay? So predict the speed up. Speed up here is this, the one that we think is going to attain, but not really is this one. Actually, it's the one. This one is the one that we're going to attain. Okay, example. Let program have 40% of this code enhanced. Okay, when you see this 40%, you know that Fe must be 0.4 because this is the one that's given, right? And it yields the speed up, the system speed up. Actually, you should say overall speed up rather than system speed up. Okay? Because the term that we use is overall speed up. The overall speed up is the actual speed up that we will get. Or, I mean, the maximum speed up that we can get, we can obtain. Okay, that's the overall speed up. The overall speed up is 4.3 times faster. So this is the overall speed up. Okay? This is also a speed up. Huh? But this is not the overall speed up. This is the one that we think we can get the speed up, right? This is the overall, the actual maximum. So what is the factor of improvement? Fi of the portion enhanced. Okay, it's very simple. You just use the formula, just move things around so that you get your Fi at one place. Okay. Now, remember I mentioned to you that you should also check to see whether your answer is correct or not. Right? And here there's a problem. Okay, so the first question is, can we get this or not? Okay, can we get it? Because it says here, our S is 4.3. We want to find what is this n in order to achieve that speed up. Okay? Now remember I mentioned to you, if it increase, it does not increase linearly. Somehow it will saturate, right? Okay? You can saturate here. But the question asks you, it can be here, it can ask you here, which you have a solution. You can ask for this, where you can have a solution. But then if you ask for this, there's no solution there. You cannot achieve this. You cannot. I set this speed up. I ask you, can you achieve it or not? So you have to go and find out first, can you achieve it? Okay? Can we achieve this? Speed up 4.3. Okay, and how do we find out whether we can speed up? Very easy. You just increase this n to infinity. Because when you increase the infinity, if we can achieve, it will reach this point. At infinity, right? And it will reach or it will exceed. Right, at infinity. So we test it by putting our Fi equals to infinity first. Our n equals to infinity. And we put it in the value, and we try to find out what is the speed up, maximum speed up that we can achieve. We want to find out what is the maximum speed up that we can achieve. And we found out that is 1.67. We found out is 1.67. That means that is the best that you can get. Okay? If your Fi or your n increase to infinity, that means this is not achievable. This 4.3 is not achievable. You get it? Okay? So you don't put in the value inside that, because if you put in value, you get a funny result. Maybe you get negative result here. Okay? So if you find out that negative result, whatever, you know that that is not the answer. Okay? Because I saw, because I have the previous lecturer to mark, and the student compute and is negative, and I cannot describe why is C negative. Okay? Actually, it's because of this. This is the maximum speed up you can achieve, but it's asking for more. Okay? I ask you, can you achieve this and find this n? But if I take this n to infinity, I get 1.67. That means I cannot achieve this. So the answer is, you cannot achieve this speed up, 4.3. Okay? So this also tells you that if your problems stay the same, the size stay the same, you increase the n to infinity, you're not going to achieve that speed up. Okay? So this is Ampere's law. So it also give you an idea when to increase the n and when not to increase the n. You try to find a balance so that you can get the best result for the money that you pay. Okay? Okay, is it the third one, this one? Sorry, this is the second one still. Predict the speed up of fraction enhanced is a continuation. But this one, actually you can get the answer. Okay, just now you cannot get the answer, but this one, for example, in case number 2, you can get the answer. So in a different case, you get, P is also 40%. That means the fraction of enhanced is 40%, 0.4. and ask you the speed up, the overall speed up is 1.3 times faster. Can you achieve it? If you can, find the N. Find this N or performance of improvement. Okay? So what you do is you just plug in the value in infinity first. You found out that it's 1.67, and this 1.67 is greater than that, so you know you have an answer. Okay? So once you verify that you have an answer, then now you can use the original equation, and then you just plug in the value, and you find what is the value. And you found that the value is 2.367. Okay? And you can see this 2.337 is actually larger than this. You should also show to you that it's correct, because this is what you imagine you can achieve. This is what you actually achieve, the maximum that you can achieve. Sorry, right? When I say this is what you can achieve, actually I say it wrong. I should say this is the maximum that you can achieve. Okay, it's the maximum, not that you can achieve. You might get less than that. Okay, but that is the best that you can get. You cannot get better than that. Okay, the third question. The third part of the question. You want to find the fraction of enhance given the fraction of improvement and the overall speed up. Okay? So this one is also you need to find out whether you can achieve or not. So what you do, you find the value of the speed up when your fraction of improvement is infinity. Okay? Once you put that value, you check, and you see if it is the value that you are able to get. So 0.929, and it's asking for 3.3. Check your work. Determine the ME, right? So after you determine the ME, okay, then you plug it back in this value, plug it back in, and then you find out your answer. Okay, your answer is 3.3, so that actually you can achieve the performance gain. Okay. Okay, this is the last part of this. The next part actually is not talking about this anymore, and that is the last part. Okay, let's look at this Gustav-Hong laws. Now, Gustav-Hong law is, as I mentioned before, if you use your problem size, fix your problem size, this is what you get. In order to combat this, you want to increase further, you increase the problem size. The reason why he came up with this is because he found out that when he studied the equation, he said he discovered that as you increase the size, the problem size, the zero part fraction doesn't change. Okay? Only the parallel part you can improve. Okay? So the amount of fraction, because the code is the same, right? Am I right? If your code is the same, the S and the P is always the same fraction. Okay? But if your problem size increase, then you increase the N. And you look at the equation, doesn't N actually increase and you get performance gain, right? Okay, that means you will put more problem, that means your problem is not fixed, your problem is keep on increasing, your N can also increase together. And you will still get the performance. That means you will get this S shape also, but this S shape is going to enlarge. Okay? Because your problem size is bigger and bigger. Right? So your limit here is not there, but your limit is somewhere around here because the problem size is already in scale. Okay, unfortunately there is no example to compute this. Okay, and let's say the question will come up, it will be as simple as this. Okay, the one that you put maybe is like investor. But more practical laws is actually Gustav-Hong law. Okay, the next topic is about how can we improve your GPU and do not have any problem with memory store. Okay, memory store is a problem. Theoretically, if you exclude this memory store problem, you think that you can actually run the code and then you can get performance gain. But when you run the code, you don't get that performance gain that you expect. Okay? One of the reasons is because you got memory store. And we will use this histogram example to demonstrate. Okay, let's talk a little bit about histogram so that I can explain what we're going to face later. Okay, histogram is basically try to extract notable feature or pattern from large data set. So what you do is basically you have a large data set that is very hard for you to see. So what you do is you create histogram. Histogram is nothing but to put it in a bin. Okay, you take a range, some range here. Okay, you set a range, let's say 2 to 3, 3 to 4, 4 to 5, or a larger range. And any number that is fall within there, you just bin it. Okay, you bin it. And then you count how many. So the number that you count here will be the value for that particular part. Okay? So if you count how many there, maybe you get up to this point. So that is for that particular part. So eventually you get the histogram. So histogram is actually to do that. Okay? And one thing good about this is large data set normally you're not able to see it. So if you bin it like this, then you can see some pattern. Okay? Because if you combine the result and then you visualize it, you can see certain pattern. Okay? People use this for fraud detection, credit card especially, for some kind of transaction. Okay? For example, you see this particular part or area, you see a lot of people using credit card. Right? Why is that so? Maybe there's some kind of pattern, so you bin it and you can see some pattern there. And then you go and investigate. Okay, so a lot of people use histogram technique in order to find some fraud in there. Just now, somebody did the histogram one, but that is for image enhancement. Okay, it's something similar, right? Because it's actually extract the feature, you try to enhance it. So you use the histogram to enhance the picture. Okay? Use the
Different from what I thought. Different from what I usually thought it would be. I thought histogram is like, you divide the image into many small histogram together.
what I described to you, right? Divide it, and then you count how many there. Okay, but what I'm talking here is after you do this, of course, what is the use of that? You can use this for this many different things. Feature extraction, like just now, is feature enhancement. Okay, you enhance the feature. And you can use it also for fraud detection. So there's a lot of use of this histogram. Of course, histogram you can use for many other purposes. For example, study of your data. But you can also use this and use it for this. Okay, and you can correlate as well. For example, certain pattern you correlate to other pattern or the previous pattern. You can see whether there's any trend that is similar. Okay, which you can extract and study. Okay, so that is histogram. Basically, is just binning. We call binning, or A to B. How frequently it happens, and you just bin. Okay. All right. Now, the question here is not to solve anything, but how do we do the binning? Use parallel computing. And one of the problems with this, although it's useful, and that's why we talk about it, because it can be used for many purposes, right? And since a lot of our algorithm, especially just now, we have already seen one example, which use histogram technique to enhance the picture. But if you don't do it properly, you get memory store. Memory storage is bad because it will decrease the performance. Okay? So you have to do it in certain way in order to avoid that memory storage. Okay, you have to partition the input into section. There is the key to the parallelism because you have to decompose it. And you have each track to assign to each of the track. It's common sense. And each track iterate through the section and do the job. In our case here, this simple example we will see is to extract each letter and increment appropriate gain counter. This is this problem here. Okay? So this is the histogram of the problem that I want to discuss. Let's say I got a text full of characters. Okay, and then I want to find out if I want to bin this four letter section: A to B, E to F, I to L, and M to P, and so on and so forth. Actually, but I'm only interested in this time. Okay, for each of the characters in the string, I will increment the bin as I check the text. Okay, and this is what we should do. You all know that. And one of the ways to do it, okay, I'll show you two ways. The first way, we're going to, because our text is going to be like this, programming massively parallel processing, suppose. And I use thread 0 to do this. I use thread 1 to do this, thread 2 to do this, thread 3 to do this. Okay? And they will try to bin it. So this three thread is processing different part of the data, and will try to increase this number that is binning, right? Binning the characters. Now, if you do that, you got a slight problem there, because this data actually is not common. Okay, they are quite far apart, and GPU has problem with this, especially if the size here is big, right? Because it has to grab the data from very far apart. Okay, grab it into the memory and process it, and GPU is going to suffer. Okay, if we don't have that physical limitation, of course theoretically it should get the same answer. But in GPU, don't do this. It's trying to tell you that. Okay, or in any cloud computing, we don't do this because we have limitation with our processing if the data is very far apart. Okay, so we don't want to do this. That means we don't want this to be big, and then we have to grab all of them into the memory and assign the track to it. Okay? Now, if you want to improve the speed, you should be doing this. Okay, you don't want to do this. Right? This is track number 1, do this, track number 2, do this, no, don't do this, you do this. Okay? Because when you take the data, you take this part of data in. You don't read the whole thing, you read only this. When you read this, then you assign 1, 2, 3. So they're all busy, even though the memory is small. And once you finish that, you're done with it, you save it somewhere, and then you get the second part in. And then you assign 1, 2, 3. Okay? So the equivalence of that is this. So instead of doing like what I mentioned just now, you don't read 3 or 4 different sections, you read only one section. And then you assign this to track number 1, track number 2, track number 3, track number 4. Of course, this is too much. Normally don't do that. Normally you take maybe a little bit bigger. Maybe 4 for track number 1, 4 for track number 2, 4 for track number 3, and so on. And this one can fill in the GPU memory. Just enough to fill in the GPU memory. And that's what you do as well, right? You put it in the chunks, but you don't read all the chunks. You read one chunk, and all the track is going to do that particular chunks. Yes. So basically, you're doing this. Okay? So if you want to have improvement, you try this method rather than that method. So that is the end of this chapter. Okay, next week we will not have any more lecture, but we will have still practical. Okay? So next week will be still your assignment presentation. And hopefully I can get the marks before next week is 14. Week 14 already, right? So I need to get the marks already week 14. Okay? That means if you missed it, that means you have to do outside the practical time. Okay? That's why I want all of you to present just now. Okay, don't go missing, because you go missing, you lose the 10 marks. Do you know that there's a 10 marks for your presentation? Yeah. Okay. Right. Another thing is I need to perhaps give you some more exercise so that you can prepare for your exam. Okay. The exercise will be. I'm still thinking. I'm not sure whether I should give you problem to solve and then you submit, or maybe just objective question again.
I would rather subjective question at this point.
Now you're scared, huh?
Scared already, very scared.
Okay, I will try to make it simple. Okay, I'll
So
make it
exam
simple.
simple.
Huh?
Final simple.
Final exam.
We are dead already.
Actually, it might be simple. It depends on whether we study or not. Yeah.
Final until what chapter?
What?
Final until what chapter?
That is a good question. I'll list it down. I'll list that down first. I'll let you see. And then I'll give you an extra question, and that extra question will be related to this to prepare you for the exam.
There are some
So the exercise.
that definitely will not come on that.
Yeah, because there are only 4 questions. Right? So,
Which part are exempted from the final examination?
yeah, I'll tell you which part that you should focus on. Okay?
So you give by this week.
Yeah, I'll give by this week, and also I'll give the question also by this week as well, so that you can do it in the last last week, which is week 14 next week, right? Okay, you complete that. There's no time, 1 hour time. You don't have to. I just give it to you, and then you do it. Submit. Submit before the end of next week. Is that okay?
It will count into the coursework.
Yeah, it will be counted into your coursework. And please pay attention to what you answer, because that is a hint to your exam. Okay? And it will be counted as also marks for you who did not do well in your first attempt in the test.
I think all of them.
Is it all of these? I don't think so. I saw the graph is a portion here. There's one person who actually scored very high. And then the rest maybe is at the middle. Okay? Okay, I'll give by this week, you try to answer by next week. Okay? That means you can submit anytime that you want, but then don't submit after, because of the deadline is to submit your coursework. Okay, if you have any question, you can ask in the chat, or you can ask me during the practical time. I think practical time next week I don't have time. You better ask during, outside the class.
One question about CUDA.
Yeah.
Is there a way to, how should I go about doing lessons?
Hold on, let me give you the sign code first. Okay, this is the signing code.